Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off in the previous lecture where we had rearranged some of these equations and we had separated out the variables in terms of, or rather we separated out all the components of these equations in terms of inputs, parameters, variables, and therefore we had categorized how many equations they are with respect to the number of variables. So in this lecture I'm going to continue and I'm going to talk about how we can potentially bring in the mechanical component of this simulation, which is precisely the speed and the rotor position, into these equations as well. So as always, before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures but you would like something a little more comprehensive, I do have full-length online courses that you can access on my website pythonpowerelectronics.com. So this is the homepage of the website. If you click on the button Learn, it takes you to the list of courses. So the very first course I have is Simulating Power Electronic Circuits using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the signal package within SciPy to design and analyze filters specifically for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to analyze and design controllers for power electronic applications with the specific case of a single phase converter connected to a single phase grid. And the very last course I have is called Why Specialize in Power Electronics, and this is more of a motivational course for either high school students or junior undergraduates to motivate them for choosing power electronics as their specialization, and this course talks about the challenges and opportunities available to a power electronics engineer. So the link for this page is available in the description of this video, so if you're interested, please do check it out. So with this, let me get back to my lecture. So as I already said, the purpose behind rearranging these equations is to make sure that these equations are linked to each other. Now of course this is not really an equation, this is more of a calculation, so maybe I'll move it out of this and put it somewhere else. Well, actually maybe I should just put a row here just to differentiate. And let me paste it. Oh no. So let me just paste it here. So this is just to distinguish between a calculation and an equation. So maybe I can bring these more to the left, and I can bring these more to the left also. Right. So this gives us some more space, and we can write the mechanical equations here. So the idea behind rearranging is that whenever we have a set of equations and we want these set of equations to represent the mathematical model with which we are going to simulate any system, it is extremely important that these equations have links to each other. If, as in the previous case, if you watch the previous video, you will find that I had committed an error by which I had instead said that instead of induced EMF, I had said it is merely the derivative or rather of current multiplied by the self-inductance. But the problem with that is then there is no link between these two equations and the remaining equations. Now instead, if you have a look, you will see that these two equations are linked to these two equations because we have the induced EMF term, and the induced EMF can be expressed using Faraday's law. So we are combining two laws. We are combining the Kirchhoff's voltage law and we are combining Faraday's law. And since the induced EMF is the derivative of the flux linkages, the flux linkages in turn can be expressed as the combination or this function of the stator current and the rotor current. So now if you see, there is a very nice linkage between all these three equations, set of equations. This is usually what is required because any simulation model, the variables must impact each other, and that impact can only happen when the equations themselves are interlinked. So now that we have this, the next question that we need to ask is, how are we going to bring in the mechanical component? So again, here let me start writing this. The mechanical, when I say mechanical component, what do I mean? The first and foremost thing that comes to mind is the speed. That is, let me call this omega, or rather, I don't know what I should call this. Maybe I should call this omega m instead. So this omega m is the mechanical speed, right? The reason why I'm separating this from any other omega is because we quite often use omega for the angular frequency, which is 2 pi f, right? Where f is the grid frequency. So let's put the m here to be absolutely sure that this is the rotational speed of the machine. The next thing that is quite obvious is the torque, right? This again, let me put m here because this is the mechanical torque of the machine, right? So the mechanical torque of the machine is the actual load torque, right? This is the mechanical work that this machine does. So you can kind of say this is the output torque. Now besides this, of course, there is the input torque, because remember, this machine converts electrical energy to mechanical energy, which means there is an electrical torque which is also produced. So we can call this the input torque, right? So besides this, there is one other variable, but that one other variable is not very easy to detect, right? This variable is called the rotor position or rotor angle, and we usually call this theta m. You can also call it theta e for the electrical torque, but theta m is basically omega m multiplied by the time instant. So if we know the rotational speed, in reality it is the integral of this omega. So maybe I should write that instead. It is the integral of omega m with respect to time, because remember, the machine need not be rotating at a continuous constant speed always. It will have its fluctuations, which means that the rotor speed is a continuous integration of this rotor, or rather the rotor angle is the continuous integration of this rotor speed over time, and therefore it will reflect any fluctuations in the rotor speed as well. So now that we have these equations, what are we going to do and how are we going to bring it into this, or rather how are we going to modify this or even add more variables? So the first question we need to ask is, when a motor when this rotor rotates, what impact does it have on these equations and on these parameters? This is a question which we need to ask. So now first thing we've done is, we've done all these calculations. We've done a simple steady state calculation, and you can go back here. You will see that all these calculations have never taken into account the rotor position angle. We are never considering that. So now the question is, how do we bring it in? In order to bring this rotor angle or any of these mechanical variables into either the equations or the parameters, we need to have a look at how these parameters are achieved in the first place. So let's look at these parameters. We have these parameters. Let's list them out. It is the stator. Let's look at the first two, that is the stator resistance and the rotor resistance, right? Now let's go back here to this one and let's even look at our schematic, or rather the image of this machine. So when we talk about the stator resistance and the rotor resistance, we are talking about the winding resistance of the stator and the rotor bars, or the resistance of the rotor bars, because in this particular case the squirrel cage motor consists of bars which are short circuited on both ends. It could be that this is also a wound rotor induction motor, in which case the rotor resistance we are referring to is the winding resistance of this rotor itself. So in any case, these two are basically the winding resistances of the stator and the rotor. So now the question is, if this machine rotates, what impact will it have on the stator and the rotor? So the first and most obvious impact is, as the motor rotates and as it heats up, right? Because whenever a motor starts working, it will get warm, the temperature will rise. Therefore, with rising temperature, the stator resistance and the rotor resistance will also change. There is a temperature coefficient. But does the stator resistance and the rotor resistance depend on the rotor angle, the exact position of the rotor when it is rotating? The answer to that is no. The rotor resistance and the stator resistance do not depend on the rotor angle, do not depend upon this rotor angle theta m. Right? So therefore we can say that these two parameters, the first two parameters, are independent of the rotor angle. So now let's look at the stator inductance and the rotor inductance. Now, if we come back here and have a look, what is the definition of this inductance and this inductance LR and inductance LM, or any inductance for that matter? Now, here we have already talked about it. That is, the inductance, this flux linkage we've talked about, is the sum of self-inductance multiplied by the current and the mutual inductance by the current, also by the current. But if we forget about the concept of self and mutual inductance and we just consider the inductance as a physical quantity, just as a physical quantity, when we represent any inductor or any winding or any coil as an inductance, what we are trying to say is, if we pass a current through this winding, that is a current I, and the inductance is called L. It could be called L, it could be called M, it could be called anything, doesn't matter. If there is a certain inductance L, in that case, this will produce a certain flux linkage. This is what it means. This is the definition of inductance, right? That is, a certain current flowing through an inductor of a particular inductance will produce a flux linkage. Specifically, if a current of 1 ampere flows through a inductance of 1 Henry, it will produce a flux linkage of 1 Weber turn per ampere, right? Or maybe it's not right, Weber turn per meter, sorry. So this is the definition of the inductance. So the question now arises, how do we map this to the actual machine? So for example, let's come over here and have a look. If you have a current flowing through the stator, this current flowing through the stator will produce a flux. This flux, as I already said, some of it will leak, some of it will be in the air gap and will link with the rotor. Now, what exactly is it that produces this? How is this flux produced? Again, if you go back to the basics of it, we say that whenever current flows through any inductance, if this inductance has n number of turns and the current is I, then Ni is the ampere turns. And this ampere turns, if we divide it by the reluctance of the flux path, this results in the flux that is flowing in the entire flux path. So for example, if I go back here and say, if a current is flowing through the stator, we need to find, number one, determine what will be the flux path and what is the reluctance of that flux path. So as we've already said, there are some flux paths which are leakage paths. So for example, it just leaks into the air. So these leakage paths will have a reluctance mainly comprised of the loop in the air. And since we already know that the reluctance of air is extremely low or rather the reluctance or permeability of air to the passage of flux is extremely low, the reluctance of the path through air is extremely high, which is why leakage flux is usually very high. On the contrary, the permeability of iron or many other metals, because nowadays we don't just use iron, we use alloys, many of these metals is extremely high, sometimes 1000 times higher than that of air. And therefore, the flux flowing through the metallic part of any metallic part will have a much lower reluctance, almost 1000 times smaller than that of air, which means the flux is going to be much more stronger. So now if we take a look at this entire system, you will see that if we consider the main flux path, that is the flux, if we say the current flowing through the stator produces a flux which links with the rotor, and this flux path is our main path, then in that case we need to determine what will be the reluctance of this flux path. And if we try to determine what is the reluctance of this flux path, we need to also determine how does it change. How will this ever change as the rotor rotates, and when can it change and how does it change? So now I will end this lecture here because it's getting pretty long, but the main concept is here that this question can be answered depending on the construction of the machine, on the philosophy of the machine, and also various other parameters. For a squirrel cage motor it is fairly easy, but there are some types of motors where it is quite complex. So I won't go into that much detail because we'd like to simulate gradually, maybe with a single phase induction motor, that is squirrel cage motor, and we can continue further. But for now, the idea is in the next lecture I'm going to talk about how, or rather by drawing schematics or drawing some diagrams, I'm going to talk about how this construction of the rotor will impact the reluctance with respect to the rotor position, and how we can sort of create equations or expressions for these parameters that take into account the rotor angle. So with this, I'm going to end this lecture. If you have any doubts, please do post either in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with this lecture. Thank you so much for watching and see you soon. Goodbye for now.